All right, let's take a look at population modeling using differential equations. For this particular problem, imagine a certain bacteria that exhibits exponential growth. The bacteria contains 100 cells initially and 739 cells after 20 minutes. And our question is, determine the number of cells present at any time. So in order to solve this, we're going to look at 4 basic steps. First, we're going to find a general governing equation. Then we're going to find a particular solution for that differential equation. And then we're going to go ahead and apply our initial conditions shown here to come up with a particular solution, which will really answer this question, but we're going to go ahead and plot it out as a 4th step just to confirm that it all makes sense. First thing that we need to do to figure this out is find a governing differential equation. And all we really need to do to start this first step is to define our basic intuition. And our basic intuition tells us that the rate of population growth is going to be proportional to population size. Now this isn't too complicated of an assumption to start with. We're basically saying that imagine that after 20 minutes when we have 739 cells, there's going to be more cells there to reproduce, so it's going to be growing at a faster rate when there's 739 bacteria cells than it would be, say, at the beginning when there was only 100. So basically, more bacteria means more opportunity to reproduce, means a higher growth rate. So bigger population size will correspond to a bigger rate of population growth. So that's all we really need to go ahead and find our governing differential equation. We can just take this assumption and go ahead and formulate it into an equation. So we'll call our population size P. And if P is our population size, then we can define our rate of population growth as dP dt. So this is basically the slope of our population, or how it's increasing with time. For proportionality, we'll use K as our constant. So dP dt is going to equal K times our population size, where K is our proportionality constant that governs that relationship between our size and our rate of growth. All right, so let's go ahead and move that equation up here and kind of hold it here as our governing differential equation. And given this, our next step is going to be to find a general solution to this differential equation. And thankfully our differential equation is in the form of a separable equation, so this process is actually pretty easy. But first thing we want to do is get all of our p variables on this left side and get our t variables on the right. So what we can do is divide both sides by p and multiply both sides by dt. And doing that, we get dp over p equals k dt. Now from here, we can actually go ahead and just integrate both sides. Now this is a valid step because if these two quantities are equal, if we take the integral of them, they should still be equal because we're doing the same thing to both sides. So this is a legal move. And from here we can just evaluate these integrals. So our left side we have 1 over p, so that integral is going to be the natural log of absolute value of p plus a. And for our right side we just have kt. And of course either side we're going to add that constant that we need to do for integration. But to simplify this a little bit, we don't really need an arbitrary constant a on this side and an arbitrary constant b on this side. So we can just define a new constant and make a little substitution here. So our new constant is going to be c, which will just be b minus a. So what we can basically do is translate our a and our b into this c constant here. Make things a little simpler for us. Our next sort of trick here is to take both sides to the e power. So I'm going to take natural log e to the natural log of absolute value p and e to the kt plus c. And again, we're doing the same thing to both sides, the same operation, so this equality is still going to hold, and again, this is a legal move. And if we do that, that natural log of p just becomes p, or absolute value thereof, and our right side we get this exponential equation. So before we move on, we can take a look at this absolute value sign, and you can imagine that it doesn't really make sense to have negative p values. A negative population doesn't really have any realistic significance. You can't have negative bacteria, right? So we're just going to assume p is positive. And of course, if we assume p is positive, then that absolute value has no bearing on this because it won't change anything. So we can go ahead and just get rid of that absolute value. And the next thing we can do is we can actually take this c out of the exponent where it's a little bit easier to deal with. And we do that by applying the laws of exponents, which means that e to the kt plus c is the same thing as e to the kt times e to the c. So we can just say p equals e to the kt times e to the c. And lastly, we can make another substitution because, of course, c is just an arbitrary constant. So e to the c is also going to be an arbitrary constant, which we can go ahead and define as p naught. And we'll see in a minute while we're defining where we're calling it p naught. That seems like maybe an odd letter to choose, but hopefully that makes sense in a minute. So with this, we've finally arrived at our general solution, and we can go ahead and write it in up here and kind of leave it there. And we can go ahead and clear some of this out, make some space here. And our next step is going to be to find a particular solution. And we're going to find a particular solution by applying the conditions given up here, specifically that we have 100 cells initially and 739 cells after 20 minutes. So let's take a look at the first one first, our initial condition. The bacteria contains 100 cells initially. So what this is saying is that the population at time t equals 0, or p of 0, is going to be equal to 100. So we can write that out here. Then we can set 100 equal to our general solution when we plug in this 0 for our t. So bringing that down, we have 100 equals p naught e to the k times 0. And now this makes it easy. We can actually solve for p naught, and that's going to be 100 divided by e to the k times 0. And of course, e to the k times 0 is going to be e to the 0, which is just going to go to 1. So our p naught is just going to be 100. And this, of course, is why we called it p naught, because in this case, the constant p naught is just equal to our initial population at time t equals 0. So what we can do now is just take this 100, and we can just go ahead and move it up in here for our p naught, and we can get a bit more specific of a solution here. That's going to equal 100 e to the kt. Okay, so we're making some progress here, but we still need to figure out what this k is. So in order to find what k is, we have to look at our other condition, 739 cells after 20 minutes. So let's go ahead and take a look at that next. And what this is basically saying is our p of 20, or our population at time t equals 20, is going to be 739. So we can set this 739 equal to our population equation here, where we have plugged in 20 for our t value. So plugging in that 20 for our t here, we actually get one equation with one unknown, which is k. So we want to try and isolate k now so we can solve for it. So to do that, we can first isolate e to the kt. So we have e to the k times 20 equals 739 over 100, which is just going to be equal to 7.39. And our next trick here is just going to be to take the natural log of both sides of this equality, which again is a valid move because we're doing it to both sides. Natural log of this equals natural log of that. And when we take that natural log, this e to the 20k is just going to become 20k because the natural log and the exponent are just inverse operations. So dividing by 20, we can solve for k, which is natural log of 7.39 over 20. Now we've finally arrived at all the information that we're going to need. So we can take this value for k, and we can go ahead and plug it into our population equation up here, and we finally arrived at our particular solution given these conditions that we've applied up here. We could also take this k value and plug it in up here for a differential equation, and we could kind of modify that a little bit too, get a little more specific. So our dp dt is going to be equal to this value, we know. So let's go ahead and clear some of this out. And we've really finally now answered our question, determine the number of cells present at any time. Well, this equation here for p tells us that. We have population size as a function of time, t. But let's go ahead and plot this out first for fun and also just to make sure this makes sense. So if we bring in Desmos here, what we're seeing now is a slope field. So our x-axis here is going to represent time in minutes, while our y-axis here is going to represent population size, which is going to be a function, of course, of our time. And each of these little lines here represents our slope field of our differential equation. What you can see up here, our differential equation is really just a function of p. It's not a function of time. So for any given p value, say our population is 500 up here, no matter what time it is, it's going to have that same slope. It's going to have that same dp dt, because given a certain population size, that's going to determine how much reproduction resources are available, which is going to determine that growth rate. So we can go ahead and plug in our specific solution, and that is shown here in the red. And you can see that if we look at when t equals 0, we're pretty close here. Look, it's about 100, right? So that was our initial condition, so that matches up. And if we look further up here, when t equals 20, we get a value of 739, so that matches that other condition that we applied. So we can see that sort of our endpoints here match, and you can see that along the way that this line is actually matching the slope of those black lines around it. So you see that our equation does match the slope field. So everything looks to check out, and it appears we found a valid equation for modeling the growth of this bacteria. We could also use this Desmos plot to show how the population is going to vary for different initial population sizes. So as I vary p0, you can see that we'll get these different curves. And of course, if we get an initial population of 500, it's going to start at a bit of a steeper curve. It's going to have a higher rate to start off with. And of course, it's always going to follow these slope field lines. And you can see that works for up to here. Of particular note here is where initial population equals 0. That's right here. And you can see when p0 equals 0, we have a flat line, and this is called a equilibrium solution. And it's called an equilibrium solution because this is the population size at which the population won't change as time increases. For this case, that's simply p0 equals 0 because, of course, if there's no population, there's nothing to facilitate reproduction, so there's no growth rate. So hopefully that makes sense. But this is going to conclude our look at a simple population growth model using differential equations, and hope it was helpful.